Aircraft designed to approach the speed of sound look different from low-speed aircraft. To find out why, let's first consider how sound itself travels through air. Slowing down the picture shows how the sound is produced. The vibrating prongs give the air a succession of pushes. And like pressure waves along a spring, these sound waves travel on through the air. The air is alternately compressed and rarefied, and as each wave passes, there is a brief disturbance. Sound waves are pressure waves. Like ripples on a pond, they spread out from their source in all directions at the same speed. All small disturbances in the air, whether audible or not, travel outwards at this same speed, the speed of sound. What is this speed? Here is a convenient source of sound at sea level. Let's measure the time it takes for the sound of the explosion to travel 1 mile, the distance between these two forts. The flash is coming now. 1, 2, 3, 4. The sound took just under 5 seconds to travel the mile. That is, at sea level, the speed of sound is about 760 miles per hour. The exact speed depends effectively on only one factor, the temperature of the air. The higher the temperature, the faster the sound travels. On a really hot day, it may reach over 800 miles per hour at sea level. But temperature falls with altitude until the stratosphere is reached at about 36,000 feet. Above this height, the temperature remains constant at approximately 60 degrees centigrade below zero. So the speed of sound is lower, only 660 miles per hour. What has the speed of sound to do with high-speed flying? To find out, let's consider first a single point, sending out small pressure waves continuously. Each wave travels outwards of sound. Now suppose the point itself is moving. If its speed is less than the speed of sound, the pressure waves still travel out ahead. But if the point is traveling at the speed of sound, the pressure waves cannot travel out ahead of it, for the point is traveling as fast as they are. If the point travels faster than sound, that is, at supersonic speed, this happens. But we're not going to deal with this case here. This is the kind of way in which the speed of sound affects high-speed aircraft. And therefore, at high speeds, the exact relation between the speed of an aircraft and the speed of sound is important. But remember, the speed of sound varies with temperature and therefore with altitude. It's considerably lower in the stratosphere than at sea level. The ratio of an aircraft's true airspeed to the speed of sound where it is flying is called the aircraft's Mach number, after the 19th century Austrian physicist Ernst Mach. It is usually shortened to M. At high speeds, it is essential for the pilot to know the Mach number, and Mach meters are fitted to all high-speed aircraft. This is how an aircraft's Mach number is calculated. The aircraft has flown 6/10 of a mile in the time that a sound wave has traveled 10/10 of a mile. It has flown at 6/10 of the speed of sound in the same atmospheric conditions. So its Mach number is 0.6. This aircraft is flying at Mach 0.9. Aircraft flying at the same true airspeed but at different heights will have different Mach numbers, for the speed of sound is different in the two cases. The Mach numbers at which an aircraft is intended to operate have a great influence on its design. An aircraft is much more complicated than the point source of pressure waves we saw earlier. So the behavior of the air is more complicated too. To find out about it, let us consider the airflow around a wing. This wing section is symmetrical like most modern wings. It is in a typical flying attitude. The air is slowed down at the nose to form what is called the stagnation region. It speeds up as it passes round the curvature of the wing. It slows down again towards the trailing edge. These changes of speed cause changes in the air pressure. The yellow regions showed reduced and the green increased pressure. All these variations in pressure together produce lift and drag. Now each point on the wing acts like a point source. Here we're only showing a few such points. Each sends out pressure waves which travel at the speed of sound and reach the air ahead of the wing. We can use smoke to show how the air flows. The influence of the pressure waves traveling ahead can be seen from the way the streamlines are deflected well ahead of the wing. Lowering a flap changes the entire flow pattern around the wing and affects the airflow ahead. We can see this better with a single streamline. Mark its position well ahead. Even at a distance, the streamline changes direction. The effect of the pressure waves on the air ahead is of great importance. It smooths the flow past an aircraft flying well below the speed of sound. But what happens when approaching the speed of sound? The airflow speeds up as it passes over the wing and reaches its maximum speed at a certain point. The Mach number here will always be greater than that of the aircraft as a whole, called the flight Mach number. As the flight Mach number increases, so does the local Mach number at the maximum speed-up point. Eventually, though the aircraft as a whole is flying at less than the speed of sound, just at this point on the wing, the air is moving at the speed of sound. The flight Mach number when this happens is called the critical Mach number of the aircraft, usually written M crit. For any wing section, M crit will always be less than 1. Aerodynamically, the critical Mach number is very important, for the aircraft has reached a speed at which it meets mixed airflow, part subsonic, that is less than the speed of sound, part supersonic, greater than the speed of sound. It is the beginning of the transonic speed range. From the behavior of the aircraft, the pilot has no way of telling that he has reached the critical Mach number. But soon after it has been exceeded, things begin to happen. The Mach meter on the left has been altered, since the actual critical Mach number of this type of aircraft has not yet been released. In this picture, it is 0.9. And soon after M crit is exceeded, the aircraft starts to buffet violently. Aircraft vary greatly in their behavior above the critical Mach number. Some show violent instability, while others, specially designed for transonic flight, may be little disturbed. To find out why problems arise above the critical Mach number, let's use a high-speed wind tunnel. This one's fitted with special optical equipment to show in colors regions where the density of the air is changing. These effects can be photographed. Solid objects, like this nozzle, appear silhouetted against a colored background. When the compressed air jet is turned on, other colors appear. We have chosen red to show regions where density is increasing, and blue regions where it is decreasing. A symmetrical wing section designed for high speeds is put in the tunnel. At low speeds, the air behaves as if it were incompressible. Whatever pressure changes there are so slight as to cause no color change. But as speed increases, the air does begin to show signs of compressibility. The colors show regions of increasing and decreasing density. The red area at the leading edge is the stagnation region, where the air is being slowed down and becoming denser. Immediately behind are two blue areas where the rate of speeding up is greatest, causing a reduction in density. This diagram will remind us of what's happening. As the flight Mach number increases, the flow at the point of maximum speed up on the wing reaches Mach 1, the speed of sound. The wing has reached its critical Mach number. And when this is exceeded, a sudden sharp region of increasing density forms on the wing just behind the point of maximum speed up. This is a shock wave. It is a sudden jump in the pressure of the air. It grows and moves back as the Mach number increases. Shock waves can even be seen with the naked eye in certain atmospheric conditions. Watch them streaming back from the nose of this missile. There. This time we're going to hold the picture still for a few seconds. Let us see a shock wave form again in the wind tunnel. A diagram shows what happens. At the critical Mach number, there is a point on the wing where m equals 1. At higher speeds, the point grows into an area in which the flow is supersonic. That is, where m is greater than 1. Outside this area, the flow is still subsonic. m is less than 1. The rear boundary of the area is the shock wave itself. As the aircraft accelerates, so the area of supersonic flow increases and the shock wave moves back, growing larger and stronger. A shock wave at right angles to the airstream is the means by which the airflow suddenly decelerates from supersonic to subsonic speed. How are shock waves formed? On the rear part of the wing, every point, such as this one, sends out innumerable tiny pressure waves at the speed of sound. In the forward direction, these waves meet airflow in the opposite direction and make less and less progress until they reach a stage where they can't travel any further forward because the airflow itself is moving backwards supersonically. It's like trying to step off an escalator going the wrong way. The pressure waves constantly pile up here, and this is the shock wave. A shock wave is a very narrow region, about 1/10,000th of an inch thick. Across this region, the supersonic airflow is violently reduced to subsonic speed. Much of the air's energy of movement, or kinetic energy, is dissipated as heat. The temperature of the air rises suddenly as it passes through the shock wave. There is also a sudden rise in pressure. The energy wasted as heat in the shock wave must be continuously supplied by the engines. Otherwise, the aircraft would decelerate. So as the aircraft approaches the speed of sound, it meets an additional kind of drag called wave drag. Wave drag is a large proportion of total drag at transonic speeds. As the speed of airflow is increased still further, the region of supersonic flow goes on growing larger, and a second supersonic region starts to form on the lower surface of the wing with another shock wave. At speeds approaching the speed of sound, the most important result of the shock wave is to cause the airflow to separate from the wing's surface. This is called shock-induced separation. It produces a large turbulent wake which alters the pressure distribution, lift is reduced, and the turbulence creates drag. In this aircraft, the turbulence strikes the tailplane, causes violent buffeting, and so limits its speed. Other aircraft experience such serious troubles as sudden loss of stability and reduced effectiveness of the controls. We can't see separation flush when the airflow is smooth and flap when shock-induced separation occurs. But shock waves don't only appear on wings. Speed up of the airflow occurs around the canopy and many other parts of an aircraft. Wherever it's great enough, there shock waves will form. Shock waves cause a vast increase in drag and may cause serious control troubles. One way of avoiding these troubles is to put them off to still higher speeds by raising the aircraft's critical Mach number. There are two chief design methods for doing this. The first is to use relatively thin wings. That is, wing sections with maximum thickness small compared with width or chord. Thin wings in this sense can, of course, be very deep. The thinner the wing, the less the air is speeded up, and so the critical Mach number is raised. These two wings are of the same general shape and at the same angle of incidence. The tunnel speed is the same for each. As it increases, the shock wave forms on the thicker wing at a Mach number of 0.8. But not a sign yet on the thinner one. Here it comes at last, at a Mach number of 0.9. But wings can't be made too thin, or the landing speed would be too high. The other important way of raising the critical Mach number is by the use of sweep back. To understand this, let's look from above at the flow over a wing. The contour of the wing section determines the amount the air is speeded up. Now sweep the wing back. We can represent the velocity of the airflow ahead of the wing by an arrow of a certain length. We can consider this velocity as made up of two smaller components. A yellow component at right angles to the leading edge, and a red component parallel to the leading edge. The red component can be considered to flow along the span and is not speeded up by the wing section. But the yellow component flows across the section and is speeded up by it. It is therefore only this component which affects the wing's critical Mach number. So the maximum speed reached over the swept wing will be less than it would be over a similar straight wing. In particular, if the flow over the straight wing has reached the speed of sound, at the same flight speed, the flow over the swept wing will still be subsonic. The swept wing has therefore a higher M crit. The greater the sweep back, the more the critical Mach number is raised. For instance, suppose the straight wing has a critical Mach number of 0.8. By sweeping the wing back to 35 degrees, the M crit is raised to 0.98. But this is only the theoretical result for an infinitely long wing. In practice, the critical Mach number would only be raised to about 0.9. Sweepback, like thin wings, brings its own problems at low speeds, such as tip stalling. So designers must compromise between high speed and low speed requirements. And aircraft designed to fly near the speed of sound use thin wings together with sweepback to obtain a high critical Mach number. Various arrangements have been adopted, all very different in appearance. If the swept wing is too thin to contain the engines, they can be mounted externally in pods. Alternatively, the engines can be buried in the wing roots, which are more highly swept than the remainder of the wing. A special kind of sweepback is the crescent wing. Here, the sweepback is reduced in stages to avoid tip stalling. The delta wing combines a high degree of sweepback and great strength. The Delta's large wing area makes it very maneuverable and gives it a good performance at high altitudes. The simple delta shape can have many variations. Some deltas have a tailplane to improve maneuverability at the expense of slight extra drag. Today, aircraft are being designed to fly at speeds far above their critical Mach numbers. Problems of extra drag and loss of control caused by shock waves are being overcome. But for many years ahead, airliners will cruise below their critical Mach numbers. In this way, they will avoid shock waves altogether and attain long range and economy of operation. At the same time, designers will aim to make critical Mach numbers as high as possible, thus permitting passenger flight at speeds approaching the speed of sound.